Twitch stream glowing, formulas flashing, minds wide, knowledge flowing, equations on the board, numbers never sleep, teaching math and physics while the count sheep. Actual education, tune in and get schooled, flipping textbooks, breaking all the rules, from Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex, quantum theories on deck, breaking all the specs, relativity theories, worlds getting small, grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep, grazing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold, brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice.
All right, what's up, everybody?
My man.
Boom, boom, boom. Let's see. Da, da. I need this to go to here. Wow, messy. All you guys here on Saturday. What's up, guys? Happy Valentine's Day. Hope someone got you a bunch of cards and chocolates. Not gonna be me today, though. I'm sorry. David, what's up, David? What do you want to say? Big dog. Big dog. Also, why is this not triggering? There's an event for sure today. We're gonna go over quantum mechanics today. But, like, not in a scary way. Don't worry. Oh, I see. Here we go. Well, actually, I have to ask Ramtin how long this podcast wants to go for. Where's Ramtin? What are we doing today? So today's a special episode. It's called the Golden Hour podcast, where we have like fun little guests come on and just like talk about cool shit. So today we're gonna talk about quantum mechanics. I'm waiting. Amogi Wogi, what's up, dude? Haven't seen you forever. You're doing OChem tutoring, you said? I'm glad that like now the, you know, it's like the blind has led the blind, you know. Or what is it? The Padawan has become the master. Cuz I can't even fucking tutor OChem these days. But I remember when you used to ask me questions.
They grew up so fast. Baby voice? Oh dear, got baby voice going already. Alright, let me pick Ram. Tell Ramtin we're here. KKK. Ready whenever you are. Can we ask questions about some topics? Yeah, if you want to ask about, I think, well, I'm gonna let Ramtin lead this, but, it's mainly gonna be quantum. If you want to ask some questions
Related to quantum, totally can. Absolutely.
Hello.
What's up, Ramtin? Good to see you, dude.
How's it going?
Good, dude. Happy Valentine's Day. Did your
Happy Valentine's.
Did your fiance get you flowers?
Yes, my fiance got me flowers.
Nice. Look at that.
She's the flower. She's the gift I want, anyways. She herself is the gift.
Her presence is the present.
Her presence. Yeah, putting up with me is good enough.
That's a lot sometimes. I feel it, dude. Yeah. Nice.
I like force her to sit down and listen to me talk about physics. So I feel like
that's a love language in itself, dude, for sure. Absolutely.
Definitely. Yeah. For
Absolutely.
sure.
All right, nice. What's up? Good morning, Zach. Machka did well at a math competition. Good job, Matt Machka. Let us know how you did.
Bing bong, my man.
Awesome. Great. Awesome. Okay, awesome. Okay, here, let's Ramtin, I don't know how long you want to go for. I put 2 hours. You can tell me if it needs to be shorter or whatever.
Yeah.
Just
No, I think we're gonna I'm gonna try to give like a little bit of an introduction to all the
Sure.
quantum. Mostly because I've heard there's a lot of like pseudo-scientific stuff that is going on with quantum, and
Yeah.
it's like it happens every once in a while. Like during pandemic, this happened. Like, and the thing is, like, quantum gets this rep that, you know, a bunch of things that makes no sense to people.
Mm-hmm.
If you put quantum in front of it, then everyone's like, yeah, I guess that is quantum. So the goal is to kind of go over a little bit of what quantum mechanics, like where it started from.
Yeah.
So at least we can kind of see where all the weird stuff happens.
Yeah, like all these like
And
pretty
then-
pictures that Microsoft releases, and you're like, what the fuck is this shit?
Yeah, I mean, that's going to be like way more complicated and stuff. But yeah, for sure. Hopefully we'll do like an introduction to all of the weird
Okay.
concepts, and I'll make it obviously without the math of it.
Yeah.
Limited math, but you know, if we ever want to do, I feel like these initial few times I want to do without all the math.
Yeah, no scary math.
And-
It's like an intro,
then
like this is what it
Exactly.
is. Yeah.
Yeah,
And
and
then-
if we ever want to go into the math, then you know that's going to be a lot more than 2
Yeah, we can have a
hours.
look at a follow-up stream on that. David was
Yeah.
asking, is quantum mechanics related to quantum numbers in chemistry, like the Bohr model?
That is a very good question, and yes, that is related to that. And you know what? I feel like that's a good question, so I'll leave it for like the end. Maybe I'll have everyone like ask some questions if they wanted to ask, and then we'll like kind of get
We'll
into
relate them,
it.
yeah, because we gotta walk before we can run, you know.
Exactly. Now, do you have the whiteboard? Was it that like?
Yes.
I kind of feel like this one's for sure. I want to like draw some
Okay.
diagrams.
Okay. You know how to log in?
So,
Do you remember how to log into this?
I do believe.
Okay, I'll send
let
a
me
link.
see.
I'll DM it to you again.
I think is it the group? Yeah. Actually, I think I'm.
There you are. Yep,
I'm
you're
good,
good.
actually.
All right, then let me give you presenter.
Yeah.
1 sec. All right, now you're presenter. Yeah, cool. You should be able to draw stuff now.
Okay. All right. So, I guess the first couple of things that we want to talk about. Let me actually. Let me find the couple
Is
of
anything smaller than
experiments that-
Planck? Planck is cool. Planck time. Planck time is like the refresh rate of the universe.
Yeah, you can think. I don't even know if.
I think there's
That's
a
like-
C in it as well, though, right? It's like Planck. It's like that, I think, technically.
Could be.
Planck. Yeah, there's like Planck time and like Planck length, and I think it has to do with like the Heisenberg uncertainty principle. Like, there's what are like the smallest measurable units of like distance and time, because they're all related to each other.
Oh
somehow.
yeah.
Yeah, and it's like proof
Yeah.
that we live in the Matrix in like a simulation. Because like why is there like a set like, you know, minimum DT that happens in life? It's pretty cool.
Yeah. Sorry, I'm just looking at some of the notes that I've had. Okay. Yes. So let's take a look at like a couple of different examples of where quantum all like started off.
Mm-hmm.
I actually used AI as well to kind of
Mhm.
do some diagrams. Let's see
Don't
if
tell
I
Zach.
can put
Shout out,
these
Zach.
ones up. Is this the one? Oh yes. Okay. So the first one, we're gonna start off with like the double slit experiment,
Okay.
because I think for this one is like kind of a thing that we see a lot. It's a name that pops up a lot in quantum mechanics. So the question is, what is the double slit? So,
Yeah.
Let me just make sure. Yeah. Okay. So, wait, is this not on?
Yeah, this is me
Connecting
drawing.
the pad. There we go. Yeah. Come on, pad. Oh, there we go. Yes, it's
Nice.
working. Okay.
Okay, perfect.
So let's start off by having like some sort of a flashlight, like right here.
Mm-hmm.
And we're starting off a little bit big, right? These are what we call like macro scales.
Big picture.
And big picture, exactly. And so we have some sort of a wall out here and a barrier that blocks this light with two slits that are going to be placed in front
Mhm.
of this light with another barrier. Now, if we turn on the flashlight, the question is, what do we expect to see on this back wall? Like, what sort of a pattern do we expect to see in this back wall? Now, most of the time, and this is, let me see if I can put this picture.
Yeah, you can copy paste stuff into.
Most of the time, we expect something like,
Ooh, I like that. That's
Yeah.
cool. Here,
Can
move
we-
that around.
can I move this? Oh,
Yeah, but you hit S, you can select and
Okay.
move stuff.
Oh, okay. There we go. Yeah. So we expect to see something like this.
Yeah.
This light kind of just it hits the back wall, and it's got these sort of like really bright spots back in on that back wall. And
Mhm.
now this is actually technically what we do see most of the time when we do take a look at the flashlight in the experiments, like let's say we wanted to do at home.
Yeah.
But if we wanted to make this more on the micro scale or like the quantum scale, the question becomes, what if these slits that we had in here, these points out, what if these were like very, very small? So instead of allowing, you can see it here, there's a whole like stream of light that is going through this.
Mm-hmm.
What if we were to limit it so that not a lot of light would actually go through that? We're just trying to get like a sliver of light to go through.
Like, we restrict it to like one like single beam is allowed to go
Yeah,
through.
exactly. Like something like that, which is like almost like a single beam. Now, most of these we're saying like we don't even know anything too much about the nature of light, and this is the picture that we expect to see.
Yeah.
Now, if you actually do that, you start to see like a pattern that you end up getting some bright spots
Mm-hmm.
that are distributed like this. So there are like some dark and light spots separated from each other by a certain distance,
Mm-hmm.
and these ones are actually able to be visible in light. And so you might ask yourself, well, how does the light get to this? Like if it travels like a straight path from here to here,
Yeah, how are we getting
How
all
does
these multiple dots everywhere?
yeah, exactly. How is it getting to here? And this is exactly why this picture doesn't quite actually work with what we expect in terms of what light does. So we say like, okay, let's actually, instead of thinking of light as some sort of a this is an animation. To be honest, I wanted to like do it at different points, but it doesn't work great anyways in terms of like the adjustments.
Mm-hmm.
But yeah, for future sessions, I'll try to figure out this AI a little bit more.
Ah, okay. Yeah,
So
I think also like the slit width. Rex brings up a good question. I think it has to be around the wavelength of the light, not the frequency of the light.
exactly, yeah. So that's the slit width was a question.
Yeah, like how tiny do these slits have to be? You know.
Exactly, and that's a incredibly great question. The slit needs to be comparable to the size of the light itself.
Right.
It doesn't have to be exactly equals to the wavelength, but like if you're looking at, let's say, visible light, the visible light would have somewhere between 200 to
Like 700, I think, right? Nanometers?
yeah, 700 or 900 depending on, so 200 to like 800 nanometers in terms of the wavelength, which is 10 to the negative 9 meters. Or in other words, like if you have a millimeter, that's 1,000th of a meter.
Right.
A micrometer is 1,000th, like 1 in 1,000 parts.
1,000th of a
millimeter.
thousandth. Yeah.
Exactly. And then a nanometer is 1 in 1,000 part of a micrometer.
Yeah. It's a lot of
So
thousands.
when these slits become comparable, the size of these become comparable to the wavelength of the light, so like, you know, in terms of the nanometer in length, then you start to see this effect. And that's a very great question, because exactly what's considered too small
And like what's considered like too big.
and what's considered too big. Exactly. And when you see this, so in this diagram, it kind of shows it a little bit better. It's not exactly like
the blue one right here? This
bright.
one down here?
Yeah. And I'll explain how that works. So this assumes that the light actually propagates like a wave.
Like a ripple.
So imagine
it's like if you drop
like
like
a ripple.
like a rock in like the ocean or some shit, or like a lake.
Exactly. Exactly. That's the demo that I usually tell people. Imagine that instead of this flashlight in here, what you've really got is like something that is creating these ripples in water. So they kind of just start to ripple out.
Yeah.
But if you just follow the wave front that comes here, this wave front ends up hitting these two little spots in here. And when it hits that, then these ones end up becoming almost like the source of light.
Ah, okay.
But the thing is, we have two different ones. So like the right one's doing that, the left one's doing that. And you start to get these interference patterns.
Yeah.
So the interference is like whenever if you look at the wave from the side, so it looks like this. Then this is an analogy. We're looking at like water waves. So if we have these, if there is another wave which is in phase with this, that means that if this wave also reaches its peaks and the minimums at the same exact place, then they add up. But if we were to shift this, wait, how do I do it? Yeah, there we go. If I shift this and I move this to the right, like here, you can see that now they are out of phase relative to each other. Their peaks and the minimums are.
You kind of see it look like this, like on top of each other.
Exactly.
This kills this kills this, and you end up just getting like a flat wave. Yeah.
Exactly. So that's where it happens, where you would essentially get what we call interference. And interference is just these ups and downs being either aligned with each other or misaligned with each other. Now, at these lines that you would see here, this is the path that the light would take. Along these points, we are getting destructive interference.
Oh, okay.
Actually, there is no light, or you can also see this in terms of a water wave. Like if you actually are in a pond and do this, you start to see that these points in water are almost like nothing is traveling through them. The water is like perfectly still at these points. But then between them, you've got these other waves that are traveling. So when you look at the wall behind you, and we kind of like pretend like this is water wave, they start to hit these walls, and the maximum amplitude or the maximum height of these waves happens right at their center.
Got it.
Right, which is right here. And as you can see, light would have these sort of blaring effect, right? It's like the brightest right down the center, but it's kind of blurred out, and then it kind of slowly fades away until it starts to come back up again.
It's crazy that it creates like another wave. right? Because yeah, if
Exactly.
you have minimums and you have maximums, and then it must also vary like sinusoidally. There's another wave that gets formed.
Exactly. Now, the question that it was asked, what is the frequency or the wavelength technically, which are both, obviously they are related to each other, like
Right.
frequency and the wavelength. But technically, it's like the wavelength because it's the size of this wave that is going. When that gets like small, obviously, which is like the light, 10 to the -9. When these holes or these openings are way too big, and it allows too much light, essentially you are still getting these interference effects, but you've got multiple different sources. So these blared parts essentially overlap to a point where it seems almost as if they are entirely like bright behind these. That's
I
why
see.
in the classical model, like if you do this with big enough holes,
Right.
like
right,
really
with these
big enough
holes.
openings,
Yeah.
there's a lot of cancellation happening here and a lot of cancellation happening. But if you make a room dark enough,
You technically would see it.
would be able to see very small brightness here. But the thing is, with the light, it's very hard to do that because light bounces, right?
Yeah.
That's why if
It
like a wall
diffuses.
is white, exactly. When a wall is white and you turn on a light that it hits the wall, the reason that the wall is white is because it's bouncing off the light that it's hitting. So you need to have small enough light particles and a very thin stream of light, as you can call it, so that we don't get a lot of light bouncing, so you can actually see this effect. Now, you could arguably do this at home with the proper instruments and everything, and you just need a flashlight that is not too bright, or like a laser even.
Yeah, you need like a really fine source.
Yeah, you need a fine enough source, but like it can't be too fine as well because laser is automatically focusing all of these. So
Sure.
this sort of a wave dispersion pattern needs to be happening,
Sure.
which is great with like something like a somewhat of a focused flashlight, I would say.
Yeah. But then you somehow need slits that, so this is 800 nanometers, so that's 10 to the 2 times 10 to the 9, so then that's 10 to the -7. So it's like 0.1 of a micron, right? Microns are 10 to the -6. So good luck, right? Finding something that's on the micron level. Like, I don't know. It's very, 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 very tiny. But okay.
Yeah, so this was actually one of the first experiments that.
So how does this relate to quantum, right? Because we're just talking about light and stuff. It's cool, but like.
Exactly. So this comes up and you would say, okay, like what about like quantum? Like we thought that this is like this doesn't tell us too much about quantum. This just says light is a wave.
Yeah.
But
and it's a
this is
particle
kind
though,
of
right? Or we have to get to that next. We got to get to that next. Sorry. We haven't proven that
We
light
gotta
is a
get to that
particle yet.
next.
Okay, sorry. We've just shown that light's a wave.
Exactly. So this experiment says light is a wave, and if we assume that light is a wave, then nothing else weird is supposed to go on, and everything else is supposed to follow all of the rules that we apply to waves. And we said, okay, well, this is great. Then in that case, a light is a wave, and we don't have to worry about it. But then Einstein came around and he proposed an experiment. And this is where, again, Einstein actually is known a lot for his general relativity and special relativity, but he was actually one of the pioneers in quantum mechanics as well. So then he said, that, okay, what if we wanted to figure out what it would take for us to release an electron from like a slab of metal? So if I would, let's say I have like a slab of let's say, aluminum or aluminium, depending on
Oop.
where the viewers are. That's okay.
Okay, yeah,
Yeah.
slab aluminum. Yep.
So, slab of aluminum, and what we should do is, like, if I have a flashlight, I think it says, let me refresh. I think I was.
Oh, my bad. Yeah, I know why. One sec. I have to. Yeah, let me get that for you. There you go. You should be good now.
Okay. So if we have a slab of aluminum or aluminium, we have to be able to shine a flashlight at this, and this flashlight, which we can tune what frequency of light it would have, it should hit this, and an electron would bounce off. And so he was like, okay, well, this just means now classically, if we are looking at waves, well, and again, let's think about like a wave, like a class. When we say classical, it means before quantum mechanics. So everything that we know is like quantum, before quantum. So a wave for water, which one would have more energy? A wave that looks like about this, or a wave that looks like about this, like bigger amplitude, bigger size.
I think this one should have more energy.
Exactly, right? So bigger amplitude would mean that it would. So I see Gladiator is asking a question, and we're just about to get to that as well. So like we're gonna figure out how it would knock off the electron.
Yeah.
So what essentially we expected is that if you have a light with a lot of energy, it would have to transfer its energy to the electron, and the electron has to get knocked off. Just like imagine if you have like a tsunami, right, hitting something has to chip off. Now if we think about it in terms of the classical waves, like water, then the bigger the height or the amplitude, that's what we call it, it's like the size of it.
Yeah.
The bigger the amplitude, the bigger the energy. Now for light, what does the amplitude refer to? It would be the intensity of the light, which is how bright something is.
Right.
So if I shine a flashlight that is a little dim, there should be no electrons. And then when I turn this flashlight extra bright, then some electrons have to knock off from this.
Yeah.
And turns out that if you take, let's say, a light like a red, infrared, which has, later on we'll see, like, so we took like infrared, and they said like, let's shine a really bright infrared at this.
Yeah.
And and no matter how bright you make it for red light or infrared, it doesn't actually knock off any of the electrons. All that happens is that the light just gets reflected.
Okay.
So then, and I think there are a lot of great questions being asked as well, which we are just like going to get into it as well. And I'm going to explain like how each one relates to this. So then turns out that like, okay, it has nothing to do with the brightness of this flashlight. So then Einstein was like, okay, what if we looked at a flashlight with a different color? So instead of, let's say, red, I chose violet, right? And when he put a violet light on this, turns out that the electrons did start to jump off, and it didn't matter how dim this was. And the only thing that changed about increasing the intensity was the fact that there would be more electrons, obviously. So
like the rate,
like,
I guess, the rate at which they get knocked off.
That it would get knocked off.
Yeah.
So then turns out that, actually, in order for these electrons to be knocked off, there is a threshold that needs to be met And that threshold is not determined by the intensity or the brightness of the light,
Mm-hmm.
but it's actually determined by the frequency of the light, which is associated with like
With the
the
color.
color.
Yeah.
Yeah. So for example, infrared has lower energy than ultraviolet. So to answer some of the questions, it turns out that exactly it was the frequency of the light that was responsible for the electrons being released, not the intensity of the light. The intensity of the frequency determines whether an electron will be emitted or not. And then the intensity just tells you, well, if there's more light, there would be more electrons. So there's just more interactions. But in terms of the intensity in itself, no matter how high you make it, it will never be enough to knock off the electrons if the frequency doesn't get past the threshold of that is required for different metals. Now, someone said, is it because different colors have different wavelengths, so it has more energy, there's enough to knock it off? Yeah, exactly. So different colors have different energies. So depending on the type of metal that you're dealing with, it would have different amount of energy required for it to hit the electrons. So like then what it would happen is I think someone asked a little. Are these questions on Twitch, by the way?
Yeah.
Just
Yeah, they're
want
on
to
Twitch.
check.
Yeah.
Yeah.
Arendelle says, is there a frequency high enough that would not result in knocking off the electrons? Like, I guess there's always an upper. Like, if you
So
went
is there an upper-
too high in frequency, would it stop knocking them off?
No, it would always knock them off. It's like whether you either get past the threshold, it would start to knock off electrons.
And there's a
Right.
name for this. It's called like the work function, I think, technically, right?
The work function, yeah. And
That's the
I
fancy
think there
word
were
for
some
it.
other questions. I'm gonna like. I think if the questions are a little bit kind of like I know someone asked about quantum field theory, so that one we'll get to it maybe later because it's not quite related. But someone said it knocks off the electrons from the outer shell. Does the excess energy make the other electrons jump shells too? Yes, exactly. That is a very good observation. So the first ones that the first electrons to be emitted by this would be the electrons in the outer shell, which is what we call it like valence shell, for example, in chemistry. So those ones would be the first ones to get emitted. Now let's go as far as saying like, okay, there are certain units of energy. It's usually measured in like electron volts, which is like a very small whatever. But let's just make it a little bit simpler. Let's just pick some easy numbers. Let's say I say that it takes 100 joules, which is an insane amount of energy, just relatively for an electron. But let's say it takes 100 to knock off an electron from this, aluminum. Now, the question is, what happens if I give it 110 units of energy?
Yeah.
What would happen to the extra 10? Well, turns out that from this 10, 110 is 100 plus 10, right? So
this is like extra.
Exactly. So this 100 would get absorbed by the electron and it would knock it off, and the excess will get emitted as light.
Oh, okay. Is that because it gets
So-
transferred as like kinetic energy to the outgoing electron?
Yeah. So it would increase the kinetic energy of the electron that is being emitted, and the extra energy would also part of that. Would be emitted as light, but obviously this light that is being emitted has the leftover energy of whatever original one had.
Right.
That some of it was absorbed by the electron, knocked off the electron, and then some of it would get transferred into this new other photon or the particle of light, and then it would have the leftover energy.
Which would have
Now-
a very low frequency, right? Because the energy of the light is related to the frequency of the light.
Yes, it would have like a frequency that is much lower than the one that was being
Right.
shining on that.
And so you might
So-
not be able to see it because it's not even visible at that point. If the
It could
frequency
be.
is low.
I mean, majority of the what we call light is electromagnetic radiation,
Right.
and electromagnetic radiation, the majority of it is not visible to us, right? We have
Right.
like radio waves, microwaves, gamma rays, right? A lot of different things. So we are able to see like a very specific, very selective range of electromagnetic wave or electromagnetic spectrum, which
Yeah.
we call it visible light. But and you can see it's like 200 till 900 nanometers, and there's plenty of different radiation that lasts from like meters or even kilometers in wavelength, all the way till like 10 to the negative 15.
Yeah, like this is the spectrum, but the amount we can see is only this very small little sliver.
Yeah, exactly. And then we have the lower energy. So the lower the energy would be the longer the wavelength,
Mm-hmm.
and then the higher the wavelength. The lower the wavelength, the higher the frequency and higher the energy.
Right.
Yeah.
Yeah.
So to also get back to another question that someone asked was, what happens to the leftover energy? Would it get like result in go into some other electrons than the lower ones? Yes.
Mhm.
That means that now some of that it can bring up some of those electrons from the lower levels to the higher levels. And this is actually a very interesting question, because you can also measure how much is that energy from a lower shell to the higher shell, depending on the frequency of the light that you give them. And
Okay.
every time, in order for a jump to happen, there is a specific amount of energy that needs to be given to it. So
Yeah.
it's
This
like
is the tie into
it's
quantum.
like exactly, and that's where the word quanta actually comes from, because quanta means quantized, and these energies are actually quantized. So when you give when you hit this with like a specific electromagnetic radiation, that electromagnetic radiation, which we can call it light, but I mean, doesn't have to be visible light, that light has to have enough energy to bounce off an electron from a lower shell to a higher shell. And obviously, the closer to the atom, the closer to the nucleus of the atom, the more energy is required to bring it up to higher ones. So that's why the first ones to get released is on the valence shell.
Yeah, the stragglers. They just chill out here.
Because it also means that the bigger the atom,
Mm-hmm.
it would have more electrons, obviously. So the valence shell would be further, which is why a lot of the metals that we deal with, in order to ionize them, it's much easier when they are bigger, because those further electrons are even relatively further than something else, and so it would take less energy. But at the same time, your nucleus size is being different, so there's more attraction. So obviously the math of this is not as simple as like a
This
rule
is always
of
the
thumb.
periodic trends that kids go over in chemistry, where they're like ionization energy, right? And it goes
Yeah.
down as you go. It goes down as you go down the periodic table, but it goes
Yeah.
up as you go to the right, and that's because
Yes.
you're adding more positive charges to hold on to more of the outside. Yeah. Can light knock off
Exactly, you're-
neutrons or protons? I don't think light can knock off neutrons or protons. Those things are pretty stuck.
Knock
With
off
the-
neutrons or protons. So like you're only left. Sorry, I'm just
You're good.
eating something. Yeah. Can it knock off neutrons or protons? So does that mean that like
I think the strong
from a
nuclear
nucleus.
forces. I think so. The only thing that's holding these to these is what's called like the weak, the electromagnetic force, like weak electromagnetic
Or-
force.
Yeah, the electroweak force.
Electroweak force, which is not very strong. So that's why light can knock it off. The thing that holds these things together, which these things don't want to be held together because these are the same charge. And when you have things that are the same charge, it's kind of like trying to take two ends of a magnet that are the same right next to each other. They want to repel. So the only thing that keeps these together is the strong nuclear force, which is incredibly strong. So I don't think light can ever like knock it apart. Maybe a collider could.
Technically it can, and that's a very good question. But this is kind of like there are two issues with that as to why we can. So from a theoretical perspective, yes, that's true. You can, given enough energy to an electron, knock off a proton or like a neutron from an atom. But the amount of energy that light needs to be so immense, we do not nearly have the energy or the technology to be able to do that, right? It's pretty much like you're like, I need something that can move, like, imagine like relatively speaking, like would you be able to like design a crane that just moves a planet? You'd be like, no, we are way too far from the technology of being able to move planets just with a crane. So that's how far we are in terms of being able to create a light enough to like knock off these sort of things from them. But the bigger problem is not even just the fact that we can't do it, but to hit the light, you need to aim for specific like atoms. So you need to hit the nucleus of the thing. And the amount of precision that you need, it becomes so immense that we really can't hit things. So you just have to fire off an insane amount of very high energy photons at the nucleus of an atom, and then hope that one of these would hit it. And again, that's in the case that we are able to produce these sort of lights. And with the nature of quantum mechanics, which is based on, where in terms of the precision, there are limitations in terms of how precise we can make things. And
I think it's because like this picture is nice and simple, but in reality, the nucleus is so tiny compared to like where the electron cloud is, where all the electrons are, that it's very, very difficult to even just hit this with a single
I think it's
particle.
like the stadiums that they play like the football or like the Super Bowl in if you put a marble at the center of it, that's like the distance from like the marble to like the closest electron would be on the nosebleeds or something like that.
Oh my god.
But it's something relative to that. That's like how small it is compared to the size of the atom. So I'm just trying to go over all of the questions that we're asking. So I think the questions, for the most part, I think I answered everything.
Yeah,
so,
I think we did.
Electrons get knocked off. The lower energy levels go to the higher. Then they would get knocked off initially.
The protons and neutrons getting knocked off is what nuclear fission is, but that's a different topic. We can do nuclear energy in another session.
Yeah, yes. I feel like then it gets into, again, quantum, it's like a very in-depth topic itself. Like there's a lot of different experiments that
there are
we
a lot of side quests.
do.
There's so many side quests in quantum. Yeah,
exactly. So now one thing about quantum that became interesting is if we were to do the experiment, like the double slit experiment, and we throw a lot of singular electrons at things, eventually you start to notice something, and it's that. Can I make this?
I'm sorry. Was this here? Is this here right here?
Yeah. So if you start to throw electrons, you can see at first when you throw in like 28 electrons, this looks pretty much like what you expected, just random spots that are hitting. But as you start to increase the number of electrons that that hit the back surface. So this is going back to the double slit.
We're going all the way back.
Then
to
you start to see.
to this.
Yeah, exactly. Then you start to see that the similar pattern that we observed when light was doing it. So then this came in as a surprise because we expected the electrons to behave more like particles,
Right.
and we expected the photons to, act like a wave. Like this was, something that we already knew. There was none of that was really a surprise to anyone prior to the 1900s. All of the electromagnetic theory, which was based on the math that Maxwell did, it was all based on the fact that light is a wave, and it all worked. And even with quantum mechanics, it works. That's why it's great. But the weird part about this was, it turns out that particles, or the things we thought of as particles, like electrons, or even like small atoms, like if I start throwing hydrogen atoms at like the double slit experiment, it also follows the same exact pattern of the
double slit.
Of the double slit for light. So this came onto, we're like, okay, so it turns out there is a wave particle duality for
this is what we call
for
particle.
light, and for particles that we considered previously to be like, little marbles or little balls, like if an electron is like that. No, a particle would actually behave like a wave, and or an electron will behave like a wave. A single hydrogen atom would behave like a wave, and we can actually measure the waves of these and the wavelength of these based on the amount of momentum that something has. And momentum is actually very easy to measure because the thing we use in momentum, now this one obviously classically, but you can measure the momentum of things using collisions. So you can measure like a particle's momentum and it will give you an answer. And De Broglie came up with
that's it.
this formula, which is the momentum of a particle, the momentum that we always say it's mass times velocity, is equals to h divided by lambda. So what is h? This is what we call the Planck's constant. Now again, as I said, we don't want to like do too much math, but
Not too much math.
not too much math, just a little bit of
A little bit.
equation.
Need a light bit of math.
Exactly.
sprinkle.
So this is like the what we call the Planck's constant. And you can see that there's a lot of names that gets like repeated throughout quantum mechanics. Einstein,
Schrodinger,
Planck,
Planck,
Schrodinger.
Bohr.
Yeah. And there was a lot of this, or Planck also.
Yeah,
I think it's a German name, so I might be.
I think Planck might be correct. We like Planck. I'm like Planck.
I think Planck might be like Americanizing it for sure.
Yeah.
But yeah, like there's, and a lot of these theories are being developed at the same exact time, right? So if you're like thinking like which one came first, it wasn't really like, oh, there's a chronological order in which like the double slit happened, this happened, that happened. It was pretty much like scientists throughout the 1900s, starting from like 1905 till like, 1950s and 60s up until even now. But like there was like a 40-year period where there was a lot of back and forth, and a lot of experiments would come out that it would reshape the ideas that they had. So we are
The
seeing
golden age of
final-
physics. We call it the golden age of physics, right?
Pretty much, yeah. That was like the dream team. Like there's like the 1923 convention or like something like that, where there was just all these scientists sitting there. So there was a lot, even amongst the scientists back then, and even up until now, there's not a complete consensus as to what is the logic behind quantum. We know the math, obviously, behind it. We can do experiments based on the math, and we can get the results. And we understand quantum mechanics in terms of like, if you think of it as like a game, you can understand the rules of the game. It's very much clear as to what everything else is. But what we don't understand is like, where do these things come from? So yeah, there you go. That's like a picture that's like,
these are like this is like the Avengers squad of like physics. I think this is Marie Curie here, isn't this?
Yes. Yeah. That's
Yeah.
Marie Curie. I'm trying to figure out who I do.
Yeah, technically her last name is
Dirac.
Polish. Technically Skolotska. Is this Dirac?
No, the guy behind him.
Oh, yeah.
Yeah, that's Paul Dirac, and the guy standing behind him.
This is Schrödinger, no?
That's Schrödinger, yeah.
Yeah.
And then all the way to the right in the second row, that's Niels Bohr.
That's Niels Bohr, yeah.
Yeah, these are the ones that I very clearly know.
Is it Enrico
Einstein
Fermi in
also.
this one? I feel like Fermi.
Yes.
Enrico Fermi.
Yeah,
somewhere.
I'm pretty sure Enrico. I mean, if they did anything
Is this
with
Fermi?
quantum, they'll be.
I forget what Fermi looks like, but yeah.
No, I think the Heisenberg is in this picture, for sure. Fermi, Enrico Fermi is here. I think maybe you can look up one with like the names on them.
Yeah, here it is with names. One sec, let's get it with names. Yeah, here it is. I got it. Yeah. And they also call this the golden age of physics. It really was.
Yeah, like this is.
The cool thing is that a little bit historical, right? This was right before World War II started, and then people started picking sides because some of these scientists went to go work for the Nazis to try to develop nuclear weapons, and then some of them came to the Allies side to develop nuclear. Okay. Oh, this is Lorentz. Oh, I didn't know. Oh, wow.
That's Lorentz. Yes. Okay.
This is Planck. This is Slotowska. I know all the Polish people get upset that she doesn't use her Polish last name in this one.
Okay,
Debye. Yeah. Oh my God, Debye was here. Langmuir. He did a lot for plasma physics.
Okay.
Pauli.
Yeah, I've heard of Langmuir. Langmuir interaction, is that?
Yeah, or like Langmuir probes too. Of course, Brienne, right? Brienne zones. This is all solid state physics.
Okay.
Pauli, Schrödinger.
Yeah, so Pauli is the same guy that came up with the Pauli exclusion principle.
Exactly. Yeah. Oh, and here's your boy De Broglie.
Yes, De Broglie as well.
De Broglie.
There.
Oh, Compton scattering. Wow.
Yeah, Compton. And so yeah, like everybody who was like working on anything at a time, they were here. All the big
who has the most aura in this photo? Who's frame mogging everyone else? That's the question these kids would say.
Honestly, I feel like Schrödinger and Pauli.
Schrödinger's not even looking at the camera, dude. He's just
the fact that they are not looking at the camera is.
Yeah, is Schrödinger staring at Bohr?
If you blinked in these pictures, that was it. Forgot.
Oh my gosh! Wow. Anyways, yeah, very cool. All right, yeah. So.
Yeah. So yeah, like then all of these weird things are happening in quantum, which was, it turns out particles, they behave similar to waves that we did not expect. Mm-hmm. And waves, such as like light, behaves like particle. So depending on what experiment you're doing, and what observation you're trying to make, these things will be different. Now, to go back to this, a lot of the times the question that arises is like, why does this formula that P equals to mv doesn't work for quantum mechanics? Mm-hmm. Or why do we not see this one, Planck's constant, de Broglie's wavelength in real life?
Classical physics, yeah. So, why when I throw something, do I not just see light coming out of it somehow?
Exactly. So let's actually write down what Planck's constant is. It's 6.626, so we'll just call it 6.63 times 10 to the negative 34.
Okay. So H.
So this
okay,
H.
You got it.
Yeah, it's 6.63 times 10 to the negative 34.
They really wanted it to be 6.67, which I think is. I think that's big G. I think big G is 6.67.
I think it's one. Yeah, wait, no, actually, you're right. It's 6.67. I think so.
That's always a funny one.
So the 6.7 beam is too.
They love it, dude. Lambda's the wavelength gladiator.
Yeah, so lambda is the wavelength. I'll write it down.
Yeah, you write it. Yeah, good.
Mentioning. And this is the momentum. So, for example, for something like light, let's figure out like a visible light of, let's say, 300 nanometers. Let's figure out what would be the wavelength of that. So P is 6.63 times 10 to the negative 34 divided by what's it called? 300, let's say, nanometers.
Oh, this is like super small.
Or 10 to the negative 9 meters. So if we do this calculation, I'll just 6 point. We will get, I just want to make sure I'm getting the math right. I should be able to do this in my head, but I don't know.
Yeah, no, it's okay. I mean, you can approximate it to like orders of magnitude, right?
Yeah. So this will give us 2.21 times 10 to the negative, what was it? 27.
Yeah.
Now, if you had a 1 kilogram ball moving at 1 meters per second, its momentum would be 1 kilogram meters per second.
Yeah.
Look at the difference. This one's 10 to the
minus
negative
20. Wow.
So the thing is, it's
So
in order
small.
for you to see something like that, the reason we don't see it is because it's 27 zeros smaller than that. So sure, let's take this 1 to be our momentum. And if h is on top, so 6.63 times 10 to the negative 34, you might ask, okay, how much would be the lambda? Well, I mean, just cross multiplying this, the lambda, so the de Broglie wavelength for a ball of 1 kilogram traveling at 1 meters per second would be 6.63 times 10 to the negative 34 meters. We
That's so
can't
small.
measure this.
Yeah, we can't even see that. It's way too tiny.
Exactly. This is a Planck length. This is literally by definition what we call a Planck length as well. Right? So that's why I mean, if it exists...
So that's a good question. Does nothing exist, or is it just we can't see it? Or you can't even like detect it? If a bear shits in the woods, like, and no one sees it, like, you know, is that kind of what this gets at?
The answer is I kind of don't know. And I don't even think anybody would know, because in order for you to have the answer to this question, you need to have verified whether this exists or not. But experimentally, we are not able to make these things. So maybe it exists. Like if I throw a ball, if I see it's the Broglie wavelength, it would be like this. But the amount of error in your data, if you're doing an experiment and you're trying to look at like how much this ball wobbles, the just like a few molecules in the air would like affect the motion of this particle enough for you to not be able to fully measure this 10 to the negative 34.
Right. It would just be nuts.
So that's why doing microscopic experiments, like things that requires a very high precision on very big things, it's kind of like it creates its own problem, where you're trying to look at something very big to see if something very small exists within it, and you can't simultaneously do both. So like it's very hard for us to be able to tell whether this exists or not. But we do know, as long as things are small and live in that quantum world, like essentially their size is very small, then we can actually measure the de Broglie wavelength for a lot of these things.
Yeah.
Okay.
Super cool.
Now, now I wanted to like take a look at some of the questions people are asking. Okay, so I wanted to now take a look at another experiment which was very pivotal for quantum mechanics, which is the Stern-Gerlach experiment.
Ooh, okay, Stern-Gerlach. Let's put this on your
Okay.
page.
So yeah, this is what we call the Stern-Gerlach experiment. Now, I like to explain this like, let's pretend we're playing a game. Let's just ignore the rules of physics or whatever. Let's not even worry about what it is that we're trying to do for this experiment in terms of the real world sense. Let's just see if we can somehow, you've bought this new game online, and you're trying to figure out how this game works. So the next challenge would be, I want to see what people would think the certain outcomes for this would be, and then we'll see how that actually represents the weird nature of quantum mechanics.
Mm-hmm.
So here's So, imagine you have a machine, and this machine is set up, and just to make it a little bit still intuitive for now, this is a magnet that is set up like this. North up here and south up here. And we throw something through this from the side. It looks like it goes in like this way. And you would get 50% of outcome here and 50% of the outcome here. So what does this mean? Like, what are the rules of this game? We have a bunch of particles that are going in, and 50% of the particles end up going towards the top side of this. 50% of these end up going towards the downside of this. Now, this itself is already a little...
How does it choose which one? Yeah, what? Wait, what? What are the things, and like, how's it deciding? I'm curious.
Exactly. So now, how does it decide? We're gonna get to that. We want to like understand this without, because I feel like whenever we try to explain it, then it kind of tries to like people try to make sense of it.
Right.
In which case, we don't want to necessarily interpret too much about this. All we want to do is just want to take a look at this. So we're gonna call this like arrangement, like the Z arrangement. We'll see why. Which is the north pole is there, and then the south one is here, and then this goes over. So this is like 50% of the particles go up, 50% go down. Now this itself was already surprising when we ended up doing it, and we'll see how this becomes even more weird. If I had a bunch of particles that go through this magnet, and I had like again, we can't see the particles themselves, what they're doing. All you can do is just put a wall and see where they would hit on this wall.
Mm-hmm.
So if you sent a bunch of particles through a magnet, what we expected to see previously, again, intuitively, this would make sense, that there would be just like a smear all over this wall.
Yeah,
right.
It should. It shouldn't be one or the other, right? It should be like kind of a mix.
Exactly. And it turns out that that's not the case at all. You actually get two concentrated points, one up here and one down here.
Okay.
Now this is trying to measure something about particles, but for now, we don't want to care about what that is. All we want to know is that if we send particles through a magnet, and these are like individual particles, like we're talking like a hydrogen atom, right? Or like an electron.
Mm-hmm.
If we send them through this, it would come out with 50% of them going up, 50% of them going down. Now I'm gonna do something interesting. I'll take a device. Again, we can't see this like from the side. It's not like you can see the particles. They are so
Right.
small that we can't necessarily detect it. All we can do is just put up a wall and we will just see what percentage come out. So if I decided to take this experiment a little further, I send a bunch of particles and do the same exact what we call the Z detector. So this is still the same arrangement. North and south are like up and down.
Mm-hmm.
There's going to be two streams of particles coming out. We're just going to ignore these, right? We're just going to, like, maybe there is some sort of a way we can block all of these. So we don't really care about these ones, right? We block all of these. And we take these ones and we send them through another, like a Z magnet. So initially when I went through the first one, right, we expected what? So let's say we send 100 particles through this. How many of these do we expect to come out from the top?
Like 50%, I guess, right? Like 50.
50%,
Yeah?
so 50, right? Now, if I take this 50 and I send it through a second detector, what do we expect to happen? Do we expect these to like go up and down? Or maybe do we expect them all to go up?
I would expect it to split again, no? Or 25, right?
Yeah, but these ones have already been predetermined to...
Oh, to be up. Okay, so
be
then
up.
they won't switch, will they?
No, they won't switch. This is the 50. Still 50 comes out here, and then 0 comes out here.
Okay.
So that's great. Okay. We're gonna now change the experiment a little bit. Okay. If I take another magnet, I'm gonna call this the X magnet, and I'm gonna send 100 particles through this. Right.
People are asking why.
So-
They're like, wait, why? Why does only
Why?
25?
Because these ones have already been their state, or what we can see, or their inclination is already towards the upside of the magnet, right?
Oh, we've already like
So if
filtered
you
them,
se-
I guess. Right? You're saying that some of them are up, some of them are down. So this first thing should have filtered out the first
Exactly.
ones, right? Yeah.
Exactly. So if you already know that these are going to be all up, then if you send it through another detector, then all of the ones that were up will stay up. Nothing weird is going on.
And they can't change in between.
They can't change in between if we're just not messing with them.
We're not messing with them.
We are just like, we're not.
Think of it like
changing.
we're taking a picture, but the picture's not like changing, you know, what they are. Yeah.
Mhm.
Like we've taken a picture with this first one, and we're like, oh, these are the, I don't know, these are the people that are smiling. These are the people that are like not smiling in the photo. So if we go and like try to see it again, we already filtered out for the people that are smiling, so we should only see smiling people. And then, yeah, vice versa. We should see 0 people that aren't smiling.
Mhm.
Right. Okay.
So now we introduce a second arrangement of magnets, but instead of this time putting it up down, we're gonna put it like, let's say, left right.
Okay.
So like something like this, and then the beam is going right through the middle. So you can kind of think of it as these ones go, let's call these left, and let's call these right. Now, these electrons that you're finding, usually they are like decaying from something else, right?
Mm-hmm.
And then you would ask yourself, okay, if I send 100 through this X1, what do I expect to come out from the left and the right? So what do you think?
I think 50-50, right?
50-50, exactly. We'll get a 50-50 on this. And let's say if you wanted to take these 50 and send it through another, X detector, then all of these will also come out 50 because they have already been predetermined to be all in the up direction. So again, this also makes sense because Z and X are just matters of perspective, right? So the fact that I'm doing this experiment with what I call X or what you call Z, there is zero difference. So someone asked, what's the Z and the X? The Z ones, we are assuming the magnets are like, let's say, upright. So north and south are like up and down. And then the X one is the north and south are like sideways. So it's like left and right. So the direction in which they incline themselves would go into different direction. And now here's where we're gonna mix things up now. We've seen what happens to if they go through Z, they come out positive, let's say, and then we take all those positives and we are like, wait, are these all positive? Again, I say positive, let's say up and down, and then they're all up. Okay, if they went left and right, then we take all the left ones, we send them through the same magnet, they all come out to be left. All the ones that were left would stay left when we make another measurement on them in terms of the left and rightness, right? So now the question is, what happens if I come and I put a first detector, which I called Z, and I think someone's a little bit ahead of me. And I send 100 through these. We know this is gonna come out 50-50, right? Now, instead of sending it through another detector, which is in the Z direction, we're gonna send it through X1. So it's like the first detector is like this, like north-south. And then the second detector is like this, like
left-right.
Left-right, yeah.
Or yeah.
So now
right.
the question is,
right, this one, yeah, gotcha.
If I made a measure on the up and down one, if there is 50-50, then what do I expect? Let me make this 200 just because these numbers would come out better a little bit.
Right, okay, yeah. So then you expect 100 there, 100 the other place, yeah?
Yeah, 100 and 100.
Then the next one should be 50-50, right?
Should be 50-50.
Like left, right shouldn't be entangled with up, down, I think.
Yeah, exactly. I don't want to use the words entangled just so it doesn't get
because
any
that's
confusion.
Yeah.
But yeah, exactly.
Can't do that yet.
50-50. So now if I take these ones, and I feel like up until now everything makes sense, right? It's just every time it goes through Z, it comes out 50-50. Then I take all of the ones that are up, and now these ones are also left. So these ones, if I put them through another Z detector, what do I expect to get? Now, you might ask yourself, well, these ones that we have taken from this, these are all the ones that are up left, right? That's what we expected to happen.
Right.
So we expect that these ones, what do you...
I should get 50-0, right?
You should get 50-0, right?
I should get 50-0.
But you get 25-25.
Oh, what?
Bruh.
Excuse me?
So this is what we mean by...
So doing this, like, kind of fucked this up somehow.
Exactly. So that's the first thing about quantum that makes this experiment weird. If I want to know if this particle is up, down versus left, right,
yeah,
I can know if it's up, down, and if it was up, if I know it's up, then if I make another measurement, it stays up.
I feel like this is like a Cardi B song. If it's up, and if it's up, then it's stuck.
Yeah. I did actually see a meme about that.
Oh, really?
So, yeah, that did kill me. So I was... Wait, so you're like, okay, if I know it's up, then it's up. If I know it's left, then it's left.
Okay.
But I can't know if something is up left at the same time. I can
Right, okay.
only know its orientation in the vertical direction or in the horizontal direction.
Mm-hmm.
Right? And so you're like, okay, well, this is actually very interesting because it kind of means that making a measurement in its horizontal direction, it messes up its vertical one, or it makes it forget its vertical one.
Mm-hmm.
So now you might say, okay, well, what are these? So now to kind of reveal what this is, these are the spins of the electron or the particle that you're measuring.
Mm-hmm.
So you're trying to figure out, if I make a measurement on the spin, which is actually going to be aligned, aligned with the direction of the magnetic field, imagine it like if you're sending through the magnetic field with like a spin like this, so-called. So if you make a measurement on the up-down one, this will turn upwards because it's closer to the up than it is closer to the down.
Sure.
And if it's you're making a measurement on the left, right, then it
would go
become
left.
Like left.
Okay. But then it's equally
And-
possible to go up down on the next one. Is that kind of what we're saying?
Exactly. Yeah. So if I make the left the right
Oh.
measurement, then making the right the up down measurement has been forgotten. It's lost whatever has happened. Now even
I see.
this itself is problematic and not correct, because we're just saying this is how we like to think about things.
We need to come up with human
But
constructs.
even-
I need something that makes
Yeah.
sense, please.
Now we're gonna go one step further, and this is where things get really weird.
Oh no, dude. It's
So
gonna get really, really weird.
So let's say that we took this 200 particles, we send it through the Z, and we take this 100, and the other 100 goes down. And then we take these, send it through the X. We expect these ones to also come
50-50,
You know.
right?
50-50.
Uh-huh.
These ones also come out 50-50, so
I wonder if we're gonna like combine them.
50, 50, exactly. Now we're gonna get all of these,
Oh, what? No.
and we're gonna put it through a Z detector.
Oh.
Now what do you expect to get?
Ooh. Well, let's see. I had
Actually,
100.
Sorry.
Wait.
Sorry. I've drawn something incorrectly. Sorry. We took all the up ones.
Okay.
We sent it through the X detector.
Oh, I see. You want to clear all this. I got you.
Yeah. Thank you. Yeah. So we took all the up ones through the Z detector. The down ones we don't care about. Right? These ones go down. 50-50. Before, what we did was we only took the 50 that went through the left, and we put the left ones through the detector, and you get 25-25. If you also individually, just so that no one's confused, if you also individually take the right ones, you put it through the detector, then you get still 25-25. So there's nothing wrong about that. They forget. But what we're gonna do is, before we're not gonna make any measurements. There's no wall that these ones are hitting. As soon as these ones come out, we're gonna mix this. We're gonna mix these two together, and we're
Okay.
gonna send the combined 100 of these through the Z detector. Now the question is, how do we expect these ones to come out?
I want to try to do it with our method of the thing, right? So if I had them right, they were like whatever jumbled, and I said they were up. Okay, cool.
Mm-hmm.
And then I have some that so these are all up, but then they go through the detector, and it's like half will go left, half will go right. Oh, I see. Well, then it doesn't matter, right? Because if you're left, you still have an equal chance of going up and down. And if you're right, you still have an equal chance of going up and down. So I would expect 50-50 again. for here.
So,
I know that's
now,
like counterintuitive though, because you would think that like, oh, these should all just be up ones.
yeah, but that's exactly what comes up. They all come out.
I'm
up
learning quantum
ones.
today.
So, what does this tell us? This tells us that if I take the Z, or if I take the up ones, I make a left-right measurement, and then I took all the left ones, and then I make another up-down measurement, they come out 50-50, or equal parts. They forget what they were. They forget that they were all ups in the first place.
Damn.
After making that measurement on the left-right. But if after we make the measurement on the left-right, instead of just only sending the left ones or only the right ones through the up-down detector, because if you only send the left ones, they come out 50-50. If you only send the right ones, they come out 50-50.
Yeah.
But if you combine them, then they remember.
Oh shit. That's crazy. What? Excuse me? You like a sound effect?
Is so good.
They love it. It's a good one. The kids asked me to add it to the soundboard. I said I had to.
That's my favorite. I love that one.
Fuck.
So there we go. This is why people say quantum doesn't make a difference, right? It's not.
It's a sick joke. It's a sick physics joke.
Your phone is like too close to you now. Like your foot's gonna grow to a second one.
Oh
like
man,
everything
dude.
that happens in the quantum world. This
Left is lost without right. Very Valentine's Day coded. Okay. All right.
Yeah, I mean, maybe this is the love story. We need to rejoin all of these for them to have the memory. If you
let's go find our
you
Stern
only take
Gauntlet.
one of them, you end up like that movie with Channing Tatum. Like what was it called, The Vow or something? Like 15 years ago. But so that's the thing about that makes quantum weird. What if you miss one?
Oh.
If you combine 99?
Like, what if you don't have
That's a
all the
very-
information back, right? If you don't have the complete picture.
So that's a very good one. And this is what we call like entanglement, by the way, and not the Will Smith type. This is the entanglement. These ones are entangled with these ones. So by recombining them, like these ones, they're like, oh, I only remember if I have my partner within this. So each one of these are like a pair. Like each of these 50 members in this one has a member in this 50 ones.
Oh,
so
I see.
If you remove, let's say, 8 from here, 42 of these guys with the other 42 on these ones, they remember.
Yeah.
And then the 8 other ones that are remaining, those ones lost their partner.
So those will split 50-50 then, no?
Those will split 50-50.
Oh, that's cool.
And then the other 42 would always go up. But I'm not 100% confident about that answer, but I don't see it how it would be different. So I think that's
is that
pretty
also why like quantum computers
Yeah.
fuck up? Is because you have these where you don't collect all of them and then you get like missing qubits flipping and stuff. I know this is very far down, but I think maybe
This
that's
is-
kind of where it's come from.
Yeah, like, and here's a very interesting thing which I recently have learned. Like, yes, exactly. You have these things, and there's a thing later on. Maybe quantum is one of those things that we have to come back to. There's a lot for it
Yeah,
to be
there's a lot.
covered. So, then, what if I send one half
Extra
to
detectors and then
and then reconnect them?
I think they
then
lose
you-
their friends though.
They lose their entanglement.
They lose their partners. Oh no.
So this is a very good question. Like every time you make a measurement on something, you are making you're kind of messing with its state. So if you make an extra measurement on one of those partners when you did not make it onto the other one, they've lost their entanglement. You see that all of the 100 that went through here, they have all gone through here. So everything in here has experienced one Z measurement and one X measurement. Even though they are coming left and right, they all have been measured X and Z. So, but if you make any measurements on any of these or on any of these 50, then you've messed with their state, so they lose their entanglement with their partner. So that's the thing, is like you can't mess with their state, but if you combine them, that hasn't been making any measurements, then together they would remember this 100 to 0. Now, as you said, in circuits we have two issues. One is, and we'll talk about this, it's called quantum tunneling, which in circuits they usually refer to it as quantum leaking. Some of these particles could end up leaving your circuit, right? And why that happens, again, you can kind of see it, and there is a quantum effect for it, which is called quantum tunneling. So when that happens, it ends up like, whichever ones that stayed inside your circuit now no longer have an entangled partner for it. So you've lost information somewhere along that quantum leaking or the quantum tunnel. And the second thing, and this is the one that I recently learned, not the first part of it, we are constantly being bombarded by what we call cosmic radiation. And cosmic radiation is essentially all of this different wave that comes from space, right? You get a lot of it from the sun. You get a lot of it from the other stars. You would get a lot of it from different planets or whatever. Any sort of interaction that goes through space, it would create some sort of a radiation. And as you're sitting down, you're constantly getting bombarded by a lot of these. Now, when one of these things could end up randomly hitting one of your particles in your circuit. So no matter how good is your circuit, and you're trying to avoid outside noise or whatever, just cosmic radiation ends up messing your data eventually. And so I think someone mentioned something about error correcting codes as well. I know that there is a thing like in the classical ones. I don't know if there is one in quantum. I think there is, but I don't know exactly the mechanism of it. I try to make it even more.
They're talking about like if you could entangle with 3 or 3+ partners. I was like, oh no, we're getting into like polycule quantum. No.
No, you can't do it actually. Like you have in order to entangle.
There can only be pairs. There's only why? I guess that's a good question. I mean, it's kind of esoteric, right? But why is it binary?
Because it's always created from something else. Like when you take two particles that are entangled, there is an interaction that was made on something else that created a pair. But there's no interaction that creates a throuple, right?
Throuples are not natural.
Throuples, maybe, yeah, they're not natural. Or if they're, so, but for this one, I'm not 100% sure. This might be extra technical. But I mean, I feel like this is also one thing I really like about the audience in here, is because sometimes there's questions that feels way too simple are the ones that are actually way too in-depth. And that's the thing with quantum. It's like some of the parts that we understand so much quantum that we can, build phones, and our entire modern technology is built on quantum mechanics. But at the same time, sometimes these simple thought experiments are able to recently I learned a way that they use quantum entanglement to be able to measure the position and the momentum of a particle like very accurately, because they make one measurement on one and then another measurement out to the other, and somehow they're cheating a little bit. But so there's a lot of cool stuff that come from this. But yeah, that's exactly the thing. So I don't think that thruples are allowed or are possible, but I'm not 100% sure about that. So maybe I'll look this up actually to make sure that we have a good answer for it. But yeah, just to kind of get back into this as a final thing, is that anytime you make a measurement onto something, you mess with its state, unless you recombine them, and somehow these ones are entangled in such a way there is some sort of a interaction between them that makes them remember the fact that all of these used to be an up one.
That's so crazy. It's like it has memory, but
Yeah.
that the memory is divided, and wow, it's crazy to me. Like what?
Yeah, that's what makes quantum, very weird, obviously, very counterintuitive, right? Because it's
a
like,
mindfuck.
if I know something's up and left, it should be up and left, but it's just like, no, it's not, it forgets. And then you're like, okay, then it forgets. Then it's like, but if you combine it with its partner, then it remembers.
Oh yeah.
So then it's like a very interesting thing that would bring up about like how the nature of quantum works.
Yeah.
So that's why this one was the other experiment that really gave.
I forgot about this
rise
one.
to
I'm glad you went
weird-
over this one, because I know
Stone
the double
relax.
I know the double slit experiment, and like cool quantum waves. Yeah, this one I totally forgot about, and I remember this is just a mindfuck, dude. Sounds
Yeah.
crazy.
This is like there's this, and then there's the Mach-Zehnder interferometer, which is essentially the same thing, but that one talks about like phase changes and everything, so doesn't need to go into details like that.
Wow, cool.
Yeah. All right, let me see what else I had.
Thank you.
Oh, and okay, actually, another final thing, which we're gonna talk about, is the spectrums. So, like, spectroscopy is something that we do in physics. So let's talk about like what these things are, and we also would it answers some of those earlier questions. So earlier we talked about how somebody asked a very good question, which was, what happens if we give something, let's say we have an atom, this is the nucleus, so if sorry, one second, I'm just trying to take a look at the notes just to make sure.
You good.
Yeah, so if you have these valence shells, there are different ways that you can actually give electrons. So let's say there is an electron here, some electron here, some electron here. Now, if you were to think about like what happens if I give this electron like the right amount of energy, we said that if I give this electron a certain type of energy, what's going to happen is it's going to absorb the energy and it's going to be emitted. It's going to leave this. Now, you can actually measure that by the frequency of the light that actually it gets absorbed by this and the frequency of the light that gets emitted by this.
Okay.
Now, what about the other electrons? What do they do? So this one, it can either absorb it and come up here to this one, or maybe I can just knock this right off from its second shell. What about this one? This one can go either to here, or if I give it enough one, it can go to the valence shell, or it can also get knocked right off. So all of these are possible. And if you take a look at the atomic spectra, you get this shape. Let me.
Oh, you need to paste?
Yeah.
Yeah, so sometimes if you already have something in the clipboard, you have to right click and say like clear clipboard on the page. If you right click, you should see like clear clipboard.
Mm-hmm.
And then there you go.
There we go.
You got it.
Okay. So this is the atomic spectra that we have. So what does this tell us? If you take a look at it, like let's look at it like a little bit closely on this, just to see what this one is. Are you able to just zoom in on this just so we can see it a little bit clearer? Yeah. So for example, you're looking at helium, mercury, neon, hydrogen.
Hydrogen, Hg is mercury.
Mercury, yeah, and neon. I said helium, I think, instead of hydrogen. Yeah. So, what are these lines that we have in here? These are the atomic spectra. So, if you want to excite the hydrogen atom, and which means that this hydrogen atom is actually oscillating. You can kind of think of like a spring almost, right? This will actually release different light from it whenever it emits a certain light, which means that as it emits the light, it loses energy. As it absorbs light, it gains that energy.
Mm-hmm.
So if you take a look at the light that emits from something that is made out of hydrogen, then what you would see is that it's going to emit light at these very, very specific wavelength, which is another reason why we call it like quanta, because these energy levels are quantized. Now, obviously, the hydrogen is the simplest atom. So if you take a look at the energy levels or like the types of energy, there are 4 different ones.
Yeah.
So this also depends on from what state goes to another state. So from what valence
what starts, what it
represent.
finishes. Yeah.
Exactly. So if you're taking a look at this, the bigger the wavelength,
yeah,
the smaller the frequency,
mm-hmm.
which
and
means
frequency is related to energy.
Frequency is related to energy. So this one that we have right here, the first one in the orange, this is what it takes to knock off a valence shell.
Right, because it's the lowest energy.
It's the lowest energy, exactly. These other ones are based on what other state something else is in. And if we wanted to, for example, bring something up to a higher energy level first, then knock it off, or knock it off right away, or bring it up from something from a lower energy level to a higher energy level.
Mm-hmm.
So these will be associated with that, and you can see the mercury and the neon. So if you actually take a look at the light that comes from a certain source, let's say like for example a star, you can actually get the chemical composition of that star by looking at its spectral lines. So if you, for example, look at the sun, then you should be able to look at all of the elements that make up the sun, but through these.
Based on what the lines that come out, yeah.
Exactly. Now, if you take a look at something like this, you might be like, okay, what does this represent? This has the dark lines exactly the same spot as hydrogen, but it's got all of the light spectrum. So what does this one do? Well, this is a light source that is emitting all different spectrals of light, which means that it's usually like an opaque thing. When we say opaque, it means it's like light is passing through it. But inside of that, it's got hydrogen, and that hydrogen is absorbing these specific wavelengths of light. So this is a bright object with hydrogen inside, and that hydrogen is absorbing those light. So these ones, that's why the names are actually aptly named. These are called emission lines because the atom is emitting the light at those frequencies. And these ones are called absorption lines because it absorbs the light at those exact frequencies. And because
if it's absorbing the light, where does that energy go if it's absorbing that light?
Usually it excites the atom, or maybe sometimes it might be used for like fusing it if it's in a star.
Okay, gotcha.
Yeah. And what's it called? If you take a look at these ones, it would tell you exactly the chemical composition of any material that you're looking at. And we can actually see these in all sort of different stars. So that's why if you ever hear like, oh, we found like, some sort of a metal on this like very distant star, and you're like, well, how do we know there is that? It's because every different element would have a very specific pattern of absorption or emission lines. And from those, you can actually make up exactly the chemical element of anything.
Right. Yeah. It's super cool. It's like a magic computer gun thing. It's just like, oh, this has this in it.
Exactly.
Very cool. And I guess the other this relates to quantum, right? Because these jumps are quantized. Right?
Exactly.
You don't have a smattering or like a blur of lines in between. It's very distinct like individual lines, yeah.
Exactly. Yeah. If you take a look at any element, they would have very specific levels. So there is no like you can't be like, oh, I gave you a little bit less energy. Maybe you can go a little bit higher. It's like, no, it either goes from one specific shell to another shell, and it needs a very specific amount of energy.
Right.
And those specific amount of energies are quantized, which is why we have the name quantum.
We can show a little bit of scary math, but this is kind of where it comes from, right? This is the equation they learn. They learn in chemistry.
Yeah. So the N1 and N2 refer to what shell it starts with and what shell it ends with, right? So N1 in this case would be considered I think it's considered
this is emitting.
Negative. Yeah.
So
this might be emitting. So I guess N1 would be the one that it ends up with. Yeah.
Fascinating. And then I think this also relates to like one of the earlier questions, right? One of the students was asking like, are these related to quantum numbers we see in chemistry? Because that's a whole subject.
Yes. So for that one, it's a little bit different than these ones. So I'll let me
put this on a new page.
No, it's okay. I'll just put it into here. So let me just look up something. Who was it that asked that?
I think it was maybe Rex. I think it was Rex, maybe, or Gladiator. One of them. It was way back. It was at the really beginning. Oh, it was David.
Okay.
Yeah, no, David. David in our Discord chat. What's up, David?
Okay. So, here's the. Let me put a picture here. Is he around as well?
Yeah, he's in the chat.
That answers hopefully this question. There we go. Can I make this bigger as well?
Yeah.
Oh,
you can just.
Did it disappear? Oh no. Yeah. So, if we take a look at this, I want to make it even a little bit bigger as well.
Okay.
Just so we can. Yes.
I can zoom in on stuff, but yeah.
Exactly. So if you take a look at this, right, in that equation, so.
This thing. What the hell's going on here? Exactly.
So. And it's mostly to do with that other term like YLM. So these are a series of like I think they're Bessel functions, but I have to double check that. as well. So if you solve the Schrodinger equation, you would end up getting an answer, a general answer to it for a hydrogen atom.
And that
Now-
answer is, the probability of finding an electron somewhere. That's
Exactly.
when we mean like solving the Schrodinger equation, you're solving for like where is the electron most likely to be.
Exactly. Yeah. Where is the electron is going to be, and that depends on 3 different what we call quantum numbers. So
Yeah.
there is a quantum number n, which is what he was referring to, and that refers to the energy or the state in which something is in. So, for example, you can see that 200, all of the ones that end with 0, they have these ring-shaped types, right?
Yeah.
So that's n is equals to, I think there's even lower, you have 400.
N is equal to 3. Is there 400?
Yeah.
Oh, here's N equals 4.
400, yeah. So this means that the electron is at the energy level when, and those are the same n's, is
That's what
from
we see here.
Yeah.
Yeah.
So and when n is equals to 2, for example, we have the second shape. When n is equals to 3, we have this. So what are these bright spots? The bright spots are essentially where we would find the probability of finding the electron.
That's what I see, because that's positive. Negative. Is there such thing as negative probability? Wait, what?
I think these ones are talking about the negative value of the Schrodinger equation.
Oh, okay.
Yeah, because the Schrodinger or the psi function, this would be the state of it. To find the probability, you square it. So all of the negative ones turn to be positive as well.
Got you.
Yeah. So n is equals to 2, then would be in the nucleus. No. It would be around the nucleus. It's around those. It's around those.
It's like two. It's like two shells above the nucleus. Yeah.
Exactly. Yeah. So this doesn't quite go with the particle duality, but I wanted to just show you this. So you can see that, for example, for n equals to 2, there is only 3 different states that we have. And depending on the orientation, so L, which is another quantum number, depending on those values, you would end up getting different probability densities, which is exactly what these are. So
and then this, I think, is like M sub L is what this is, right?
Yeah, that's like the magnetic number.
Yeah, magnetic number, yeah.
Yeah. So,
yeah, these are super cool.
Yeah, so these ones, we have the n is called the principal number, which is the 2, and this is it tells you exactly which shell something is in. The simplest one is obviously 1. I don't think they showed it in here. Then 2, 3, and 4.
Right.
And then the second one would be L, which is the second number. That's called the orbital angular momentum number. So that depends on like the angular momentum of the electron.
Okay.
What that is.
It's kind of how it's spinning, I guess.
Yeah. And then the other one is called the electron spin number, which is based on whether it would be like up or down spin.
And then Monkey Man's diving into like Heisenberg uncertainties. Like you can only know the momentum or the position. You can't actually know either. you can only get probabilities.
Yeah, I think you can do like to a certain precision, but yeah, you can't know them accurately. Exactly.
You can't like actually know like, oh, it's exactly here. That's why these are all clouds, right? These are individual particles. This is an electron. It's a single electron. It's just, this is where it's most likely to be found.
Exactly. And that actually brings up something, interesting. This is exactly why we have a thing called the Heisenberg principle, is because we know electron is somewhere within that bright spot, which is what we call the electron cloud. Then you might be like, okay, we're somewhere around that. why can't we find it exactly where it is? Then if you do know its exact position, then you don't know its momentum, which means that you don't know where it would be next. So you can't predict. You can either know its exact position without predicting its motion, or you can know its motion without its exact. You kind of know it's somewhere around somewhere.
Yeah. This is a whole other thing we could do. Quantum has so many little like tentacles, like fingers. It goes into so many different fields and so many different like, little side quests. Yeah.
And then one of the analogies I came up with, this was actually recent. I was like using this to kind of explain it to my fiance as I was torturing her. But one way that I feel like it kind of would make sense. It's not exactly how we do the experiments, but it's an analogy. So anyone who's listening, this isn't like exactly how it works, but it's an analogy. Imagine you wanted to like take a picture of a car that is moving.
Okay.
Right? Now, if you were to take a picture of this car with a very fast shutter speed, right? Now, imagine this car doesn't have like a front or a back, or you can't say like the car is only traveling forward. So let's say it's like a moving box or whatever.
Okay.
If you decide to take a snapshot of this box at like an instant so precise that you can see it exactly where it is, then just from that picture, would you be able to tell if this was going right, left, or up or down? Right? You wouldn't be able to.
Oh,
but
I like that.
What if you were to like keep the shutter a little bit open? And so what you would get is like maybe this like smear, yeah. It's like a smear, like a blob, but then this smear would have maybe some sort of a like it's like those gas that's coming out of it back or something. Maybe you might be able to see that this is going up, but because it's smeared, this picture, you're not able to see exactly where it exactly is, but you can tell its direction.
I guess they call it like motion blur, right?
Yes. Yeah.
Like, here, let's get let me find an example of one. This is kind of a cool. Here we go. Motorcycle Man. Right? I guess he's completely still, but you can see that the background is like smeared.
Yes.
Right?
Exactly.
So it's like,
so
where is the motorcycle man? Is he here? Is he here? Is he here? It's like, I don't know.
Exactly. Yeah. So like when you're taking the picture, like if you have that smear, you don't know where something else is, but you can tell its direction to a certain degree.
Yeah, I can tell it's moving this way because everything's like whipped back this way. Oh.
Yeah. So I think this is an analogy that I think I would use.
I've never heard this analogy. That's super cool. It's not time dilation, no.
Yeah.
No.
There would be, but yeah, it's not due to that.
We're not getting that crazy. We're not doing special relativity.
Actually, inside of an electron, inside of an atom, they don't move that fast. Actually, this is something that they think that they are moving at like a very. You don't know how fast it's going exactly or which direction it's going. That's also the thing about momentum. That direction is also important. So it's not like, oh, it's going this fast.
Okay, so
like
it's not even like
going.
how fast it's going. Yeah, so I forgot. This is not even just speed. This is really velocity.
Exactly.
Which, yes,
and
now you have to take into account like how fast is it going and where is it going.
Exactly.
It's really tricky.
So, but inside of an atom, they move at the speed of like maybe like meters or like centimeters per second.
Yeah.
So it's not insanely fast. I mean, centimeters per second is still like a relatively quick speed for the size of an atom, but it's not moving at the speed of light.
Right.
I
think it's the bumping into each other that moves at the speed of light. That's the whole analogy with electricity, right? Like drift velocity of electrons versus like the actual speed of electricity.
Yeah, that's exactly why electricity inside your wires travel at the speed of light, because the electric field travels at the speed of light, and that's what the other electrons feel to transfer energy.
I see.
And,
Yeah.
But the electrons themselves, I think
that's a
what they
wave.
call the drift of velocity, right?
Right. Yeah.
Drift is how fast they're moving.
Yeah, drift is how fast the electrons are actually moving, which is much slower than how fast the information is traveling, right? Which is through the fields.
What about acceleration? Oh, that's a very great question again. I like Mean Machine Rex. I don't know. I think that would say my vote for him is to get some bomb coins for him, because I feel like he asks a lot of questions that seems like simple at first, but like these are the questions that like it gives you a great understanding. So if you have, so that's also one of the things. It's like if the particle is, or if the electron is thought to be like a little ball and it's spinning around the center, then it's changing its velocity, right? And from classical physics, we know that has centripetal acceleration. So technically, it has acceleration. Now, acceleration means it has to emit electromagnetic radiation, so it has to decay. So that's a very good question. That's why electron is known to be a cloud, because if it was thought of as a particle just whizzing around the atom, then it has to constantly be emitting electromagnetic radiation, or like light, which means that it has to lose its energy and fall into the nucleus of the atom eventually. But that's not what happens, right? Electron is able to maintain itself inside of its orbit. So no, technically it has no acceleration. Unless it's emitting.
Unless it's moving, why does electricity travel at the speed of light? Shouldn't electrons first be sped up a bit? They have a mass, right? Yeah, I think it's the electricity. Man, there's that cool. What's that thing called? Newton's cradle.
Oh yes. Oh,
that's how I like to
Yeah.
explain it. That's how I like to explain like electricity is with Newton's cradle. Yeah. If anyone's ever seen one of these before, they're really cool. But you can think of these as the electrons. So the individual electrons, don't move very much or very quickly, right? They kind of just vibrate a little bit this way. But the force between them, which is carried by the electric field, travels almost instantaneously at the speed of light. So that's why electricity, an electron down here at one end of the wire is able to cause an electron at the other end to move almost instantaneously, is because all this bumping into each other travels at the speed of light, even though the individual electrons move quite slowly, actually. Yeah.
I like that. I like this analogy also. The way I say it, I'm like, imagine I just have like a bunch of perfectly lined up magnets. That, I mean, it's not magnets, so I feel like, but I have a bunch of things that are like this.
Okay.
But if this one moves a little bit, then this one is like, wait, I gotta move.
Move.
This guy's like, I gotta move. This guy's like, So like the movement of how fast they tell the person or like the box in front of them to move, that moves at the speed of light. But the boxes themselves move at like centimeters or like meters per second.
Right.
Inside of your wire.
And it's not instantaneous. It's perceivably instantaneous. But yes, nothing can travel faster than the speed of light. So technically, it's like very close to the speed of light.
Exactly.
That's like the upper bound we set on life. It's like nothing can go faster than that.
Yeah. And just to hopefully this is the quantum stuff is done. But one thing I was going to say interesting about the AI that I also recently found out. So for anyone using AIs, and if you're thinking, well, what is fiber optics? Mean Machine has been
on a tear.
I feel like Mean Machine. I would say this though. I would always say that the smartest people for me, I mean, speaking of like just experience and people that I have been around with, the smartest people always ask the best questions. They don't. It's not like the people who know the best answers. Like knowing too much. I mean, obviously, coming up with your original ideas, that's the sign of being smart. But also being very good at asking good questions is like a great way to learn. because you're kind of trying to paint a picture, and I can see where it's going with this for sure. So that's exactly where I was going to say that. So where you are trying to transfer information from your computer to the AI, every time you like ask AI a question, it sends a query, which is just a kind of a message to like, you know, just do this thing, right? But a single query itself is multiple queries. So like when you say like solve the quadratic equation, it goes around. It's like, okay, look up like addition, look up this, look up that, and it's doing a bunch of things instead of like one. Now, the AIs that we are dealing with nowadays, they transfer energy. I don't know if you knew this. So this is also like I recently found out. The rate in which they transfer energy is so fast that it bottlenecks the electrons inside of your wires.
Oh, what?
Yeah. So it's like you can kind of think of it as like you get a clogging inside your wires.
Wait, so the internet is full of tubes is a real thing now, dude? What? Oh no, dude.
I mean, that's always been the thing.
The internet's full of tubes.
But yeah, like so the information needs to travel so fast and so much information that it clogs the wires, like physically, literally, with the thing. And this is one thing we need to come back later on and talk about, like the Pauli exclusion principle and like the Bose-Einstein condensate and all that stuff. So with fiber optics, you have to, you can send light and you don't get that clogging. So why does this clogging doesn't happen when you use fiber optics is, you remember those diagrams with like the up and down arrows that they do in chemistry called electron configuration?
Oh, yeah.
And it was
this, like this stuff?
Yeah, exactly. And then you're like, you can't have, for anyone's doing that, this might be an interesting part. We'll talk about more of these stuff later. But those ones are exactly the spins. And the reason you can't have two ups in the same place is because of a thing called the Pauli exclusion principle, which says that two electrons or any massive particles, anything that has mass, cannot occupy the same state as each other. So that's Pauli exclusion principle. That's why one's up,
can't
one's
have
down.
this.
Right? Yeah. But that's only for massive particles, which is why you don't just fall through your floor. If that was the case, you might be like, oh, what if we could?
We don't want to fall through the floor. Don't do it.
We would fall through the floor. But then with light, it's a different type of a particle where it has we call integer spin. Like massive particles have half spins, so like 1/2, 3/2, 5/2.
Okay, right.
Everything that has like full spins, like 0, 1, 2, 3, and then plus and minus as well. And those ones are interaction particles, and light is one of those. Now, those can occupy the same state. So you could have two things that are ups be in the same state. Which is why it's like if you had a box made out of light, you could open it and put infinitely many other light boxes inside of that. It would never get full. But with electrons, you can't just do that. The box will eventually get filled.
Oh, no way. Okay. And so with fiber, you don't get the clogging because you don't have. Oh.
Because you're able to essentially stack the photons into the same state, so that they don't have to like wait for the person in front of it or like the photon in front of it to move so that they can get there. It's like we can all travel together at the time.
Wow, that's super cool.
So that's
I didn't know that about the fiber versus the wires. I was just like, oh yeah, fiber optic, whatever. Yeah, but wait, how's that faster than copper? Oh.
Yeah. So like honestly, prior to this, it was probably a scam.
Fiber was probably a scam.
I mean, that might be a little bit cynical of me, but I think it would have been faster. But I feel like nothing that we can. I guess it's a bandwidth thing. yeah, it's a bandwidth thing and all that. But now with AI, this will probably become much more
An actual
noticeable,
issue.
because
Yeah.
AI is like trying to do a lot of energy,
Tons of data
or
all
a
at
lot of
once.
information.
Yeah, that's
Yeah.
crazy.
Yeah, Mean
Wow.
Machine Rex. He also said light has no mass. Well, depending on how you define a mass, we'll have to get to it. But like,
yeah, we
light
could
has
get into like
inertia.
energy and mass are technically a thing, right? When we get into like
Exactly.
special
Yeah.
relativity.
So like,
Yeah.
how do you define mass? And
Maybe
someone said
we
no
could do
rest
we could do a
mass,
special relativity
which is-
topic at another point.
Yeah.
Maybe that would be a fun one to like
Yeah.
check out. I think that would cover
for
a lot of
sure.
things.
Yeah. Yeah, light has no rest mass, but it still has like momentum. So
Yeah, which can get converted into mass.
yeah. All right, I guess.
Cool. I think it's a good
That's
stopping
it.
point. We did a lot of stuff
Yeah.
today. Yeah, this is really cool.
Yeah.
I really appreciate that.
Okay.
Okay, nice.
Hopefully everyone who listened enjoyed. I don't know how many people were.
We had a lot of people. Yeah, no, we had a lot of questions. A lot of people in the crowd. I appreciate all the questions. Let's give a big thank you for Ramtin for sharing his awesome knowledge on all the quantum stuff. Yeah,
Thank
that was
you.
amazing. Yeah, thanks guys. Appreciate it. Yeah, we plan on doing these like every other week. We're gonna have a fun little topic that Ramtin's gonna choose, and you know, I learned a lot from this Ramtin. Yeah, I thought I knew an amount of quantum, but I learned new things today, which I think is fucking dope.
That's dope.
Okay, I'm glad. Yeah.
Nice.
Well,
Okay.
thank you again for having me as well, and giving everyone the platform to kind of come here. And also, I really like the questions. I mean, some of the questions I kind of have to like simplify maybe a little bit, because it's kind of hard to explain these conceptually. And I think
Yeah.
that's the hard thing about quantum as well. Like, to explain things conceptually, you kind of have to like understand the rules of the game. That's why I like to talk about the Sturm Gerlach, because it's like a very simple experiment. You don't have to know the math of that to really understand. So conceptual explanations of things in that, it would be a lot easier. But in terms of the other sorts of math as to why can't we do it, it would be like, because the math doesn't allow us and we can see it experimentally. But to kind of explain exactly what that's going on, it would be a little bit harder. So like,
Yeah.
there's some oversimplification gets.
Yeah. You're the next Feynman. Someone's calling you the next Feynman, dude. Feynman was
I'm the
just
next fighter.
we love Feynman.
Okay.
Yeah, in
Well,
celebration,
I think
I
I'll
liked
do
all
that.
I liked all the questions as well. Let's do like a little giveaway for people, because I think these were like our top 3 questions, right? Me Machine Rex, Monkey Man, and Irondell.
Yeah.
Cool. All right, here I'm gonna do a
That's
little. One
it.
of you guys will win a $10 gift card for
From
asking
the-
questions from today, because I think it was dope. Ooh, looks like it was Monkey Man. Nice. DM me, Monkey Man, what you want. I'll get you a $10 gift card. Appreciate the questions. They were dope. Yeah. I like
Well,
Feynman and Ramtin. Yeah.
Being compared to Feynman is definitely a great compliment. I really like Feynman. He's like a straight. I feel like he's a good role model as a human being, and
Yeah.
thankfully was not an Epstein list. 'Cause everything-
No, although he did go to strip clubs a lot to like have science meetings. Like this guy was a
that's
real
okay.
G.
That's with him and his wife. That everybody's consenting to that situation.
Yeah,
So-
there's money being transferred. It's everyone's above age. You hope. Yeah, he was a real cool guy. Yeah, he's
Yeah.
probably I think one of the last awesome great physicists of the golden
Yeah.
age. Yeah,
Yeah, definitely.
cool. All right, nice. Okay, well, big thanks to Ramtin. Again, if you ever want to figure out when we're streaming, please go check out the Discord. So that website, actualofficehours.com. You can click here to join our Discord, and then there's a whole channel that I'll post the notes from what we did today, and then if Ramtin has any other things, he can post them. It's I forget where I put it. Oh, the Golden Hour podcast. Yeah, here. This channel will have the notes and like other things from each of the streams. If you want to keep talking, yeah.
Yeah.
You liked Rex's questions? He can have the gift card. Okay. Congrats, Rex. You get the gift card. You tell me what you want. Nice. Thanks, Monkey Man. That's nice of you. Also, if you click here on the streaming schedule, this is a beautiful calendar that has all of the different streamers on. So it looks like Math Pawn's on next. We're going to go raid him. But if you want to figure out the next time we're streaming next week, here's the beautiful calendar. Apparently it's Math Education Week. That's sick. I didn't know that, Pen. Cool. But we'll have homework
'Cause I
help
think Penn
on
Center
Sunday.
is in BC.
Is this a Canada thing?
Canada.
Math Education Week?
No, I think that's a Penn Center thing. No, it's because next week BC has the reading week. So universities in here, they get a week off.
Oh, you get like a ski week, like a vacation.
Yeah, kind of something like that. So
Oh, cool.
yeah, usually they give like one in the middle of the term. In the fall term, it's like during the Canadian Thanksgiving.
Yeah.
Which is like October, like second or third week of October, and then there's one in the week of Valentine. During.
That's so nice. You
Yeah,
guys have so many vacations. Okay, cool. All right, awesome. Let's go raid somebody. I think Math Pawn's on. Yeah, he's another awesome math streamer. So again, big ups to Ramtin. Thanks for being here, guys.
Thank you.
And we will see you tomorrow for some homework. Enjoy Valentine's Day. Hope you guys get lots of fun chocolates and cards and stuff. Great stream. Love you guys. We'll see you tomorrow.
All right, see ya.
Peace.
Peace out.
Okay.